Good afternoon, everyone. My name is André Marcomini. I am a PhD student at Federal University of São Carlos. I'm oriented by Professor Rosário Bretas from Brazil. And today I'm going to talking about potential supercapacitors made of polymer nanocomposites. First of all, I would like to introduce the kind of nanocomposite that we are producing. We're going to use polymer matrix, of course, and mix it with a high K perovskite nanoparticles. Well, the first question is, why perovskites? There are two main reasons. The first is because of its structure with intrinsic polarizability. This is the crystal structure of ceramic called perovskite. The second main reason is the simple and low-cost precursors that we are using to make the synthesis of this material. Important to remember the application of this kind of nanocomposite that we are making used to happen in AC current. So we are looking for dielectric permittivity, but in AC current, dielectric permittivity becomes complex permittivity and have two components: the real permittivity and the imaginary permittivity. Knowing that, we must know when are making a nanocomposite to be applied as a supercapacitor, this nanocomposite must be these characteristics. A material for a supercapacitor must have a high dielectric storage or real permittivity and low dielectric losses or imaginary permittivity. So this is our main objective: obtain a nanocomposite with high real permittivity and low imaginary permittivity, as higher as possible, as lower as possible. Okay, it's important to know where we are in this world of materials to be applied in nanocapacitors. In talking about that, there are two types of capacitors made of nanocomposites. The first one is when polymer is mixed with conductive particles. It's known as CD. In this kind of situation, we work near percolation threshold. In this scheme, we can understand why we use this concentration. Here, the conductive particles works as capacitor plates. So we need a tiny layer of the electric material, the polymer, between each layer, each particle. And this is a scheme illustrating these mechanisms. These conductive nanoparticles working as a network of nanocapacitors through the matrix. And the second main kind is that one we are studying in this research work. I'm sorry again. Is when we mix the polymer with the electric particles. And this kind of nanocomposite is known as DD. In this case, we work above the percolation threshold. And the reason of this is because the polarization happens in the nanoparticle, not in a part in one with a tiny layer and part in other. It happens in each nanoparticle. So in the second case, it's important we use an easy polarizability matrix, and how this mechanism works is going to help us understand why it's so important. Start to imagine we have an increasement of nanoparticle in the matrix. The author drawn in this scheme a way of contact of particles. But it's not a conduction way, it's a polarization way. It means when we have particle contacts, it's easier the polarization be induced for a particle in other one. In this detail, the author shows this happening. The polarization being induced for a particle in the next one. But even with great amounts of particle in the matrix, we see this volumetric diffraction, we have tiny layers of polymer in no contact between particles. These red circles can show, these red circles can show this kind of situation. In this kind of situation is the reason that we need an easy polarizability matrix, because the decreasement cannot be abruptly in this place. We're going to illustrate this with a graphic in y-axis real permittivity and x-axis direction in a Composites and theoretical graphic. Imagine we start in the nanoparticle. We have a value of real permittivity of the high K perovskite. And we're going to walk in through a direction composite, and we find the interface we find there a hard polarizability polymer. In this case, the decreasement is abrupt, and we stay to the polymer permittivity. The ceramic is higher, so higher than that, and the decreasement is a step function. And this is bad for the application. We're going to lose the polarization that we had before. But if we have an easy polarizability matrix, this decreasement is going to happen as a gradient function. And in this way, the next particle will have a polarization induced. So for this reason, we choose the PVDF, that is an easy polarizability matrix. This is the structure of PVDF. It's important to pay attention when we are working with this material in which phase we have in crystalline phase, because this material have many different chain conformations in crystalline phase. The three means are that, and why is important to pay attention, because the dielectric permittivity is different in each one of that. Well, as another part, we're going to use a perovskite. Now I'm talking which one. This is the stoichiometry of this perovskite that we are making the synthesis in solid state, by solid state reaction. And we did it this way. First, we mix all the precursors. These are the precursors in stoichiometric proportion, and ball milling by 24 hours in alcoholic solution, and then we get the homogeneous powder. It was calcinated in air for 6 hours in 1900 degrees. So we will be the interest phase, and that you were looking for the interest phase. Of course, you were looking for. Then we mix it with the polymer and making a casting wave. So first we make a suspension of perovskite in DMF and a solution of PVDF in DMF2 with magnetic steering, and for 2 hours at 60 degrees, and we put the suspension and the solution all together, and it was magnetic steering too for 4 hours now, but still 60 degrees. And finally, in the end of the process, we put methanol in order to precipitate the composite. After that, we made vacuum filtration, followed by drying. In order to improve the dispersion and the distribution of the particle through the matrix, we put the dry composite and more PVDF in internal mixing in these processing conditions, temperature, time, RPM. And after that, we made the samples in a transfer molding. The samples were cut in little pieces to make the dielectric. These are the conditions of molding. And the small piece, we made the dielectrical measurements. They were done in a solartron, this model. In these conditions, 0.5 volts. In this range of frequency, is important to remember the equipment gives us the imaginary permittivity versus real impedance. And then the impedance must be converted in dielectric permittivity, real and imaginary. Well, now let's talk about the results. First, we make the wide angle X-ray scattering in the powder, and we saw the interest phase was really obtained. This is the crystalline planes of ceramic material. We made a particle size of distribution 2. We got an average of 700 nanometers particle size. And we made the measurement of the electric permittivity, the real, for the real permittivity, for the polymer, pure, and for the pure ceramic too. And we observed that for the ceramic is 1,200 higher value than the value for the polymer. Well, we made a wide angle X-ray scattering in the polymer tube to see what phase was the mean phase in the material, the crystalline phase of the material, and it was alpha phase. Okay. Before start, now we have the characterization of pure materials, but start doing the mixes. We studied models to have an idea how much amount of nanoparticle we need in the matrix to get the properties of supercapacitor that we were looking for. Maxwell-Garnett is a very classical model, and this says to us we need an amount higher than 0.9 in volumetric diffraction to start, observe, and change. So it's a lot, it's very hard to process, and is not a recent model. And we start looking for other models. This is the equation that represents, related with Maxwell-Garnett model. So we find another classical model, Brueggemann 1, not recent, but a little more than Maxwell-Garnett. This is the equation that describes this model. Here we find for our system, for our values, a volumetric diffraction of 0.33 to start, observe, and change. It's a value that we can start to think is hard to process too, but we can start to think about how to do that. So we find a paper, author calls it new model. It's not so new, but it's 2007. The equation is this one, but the condition obtained by our material is the same of Brueggemann, 0.33 volumetric diffraction to start, observe, and change. So it's a reference value that can use to start. Well, but plotting the three models together, we observe to have a supercapacitor, the real permittivity of a material applied in a supercapacitor. It would be interesting using 0.5, but it gives us 76% weight of ceramic material. It's still a lot. Well, in this important to remember, this model, the three of them, don't predict the chemical interaction between matrix and ceramic. And also, the regular particles are not predicted. So, we expect to obtain higher values of permittivity with less amount of nanoparticles. Well, for this research work, what we obtained, these are the scanning electron microscopy of our nanocomposites, and this is the volumetric diffraction that we obtained to them. It's a preliminary study. Remember, we made casting and after internal mixing in order to try improve dispersion and distribution, but we still have agglomerates. This is the mass fraction percentage that we used, and this it gives to us this kind of these values of real permittivity. We can say that it was an improvement. The value increased with volumetric diffraction increasement. So it's a good preliminary result, but still not the value for a supercapacitor. But it shows that it's going to change something. Okay, and we can see low values of imaginary permittivity, and it's a good result too. In comparing the experimental results of real permittivity with two models that we studied, we can see for our fractions, we had, remember our fractions, we had higher values. So, as conclusions, we can say we have our first success was in perovskite synthesis. We obtained a high dielectric permittivity material by solid-state reaction, relative simplest process using low-cost precursors. And also, even with agglomeration, we obtained higher real permittivity values than the predicted by the models. And this was our second success. And our last conclusion is, therefore, it's expected that improving nanoparticles dispersion distribution or even the amount of nanoparticle high permittivity values could be obtained. I would like to thank the financial funding and you for the attention. Thank you very much.